Repetition, they say, is the key to mastery, which is why practicing with previous examination papers is essential to achieving those top results. I hear if you do enough past papers, you would have seen up to 60 to 70% of your own examination paper. Shh. Let's look at this one. In the diagram below, a 4 kilogram block lying on a rough horizontal surface is connected to a 6 kilogram block by a light inextensible string passing over a light frictionless pulley. Initially, the blocks are held at rest. So here we've got a two-body system, and 5.1, we want to state the work energy theorem in words. So 5.1, the work energy theorem states that the net work done on an object is equal to the change in the kinetic energy of the object. Then we have the scenario where the blocks are released. The 6 kilogram block falls through a vertical distance of 1.6 meters. So we can see that in the diagram. And 5.2, we want to draw a labeled free body diagram for the 6 kilogram block. Now, if we isolate the 6 kilogram block and we look at what forces do we have acting on that. So we know that we have the tension here pulling upward, and of course the block is hanging off the table. So we would have its weight or its force due to gravity acting downward. So those are the two forces we have acting on the 6 kilogram block. So if we have to draw a free body diagram for that, it's simple enough, and we know for a free body diagram we just use a dot and draw in our forces. So we've got the tension acting upward, and we've got our weight acting downward. So you can label it as T and W for this case. So that's our free body diagram for the 6 kilogram block. 5.3, we want to calculate the work done by the gravitational force on the 6 kilogram block. So 5.3, we want to calculate work done by the gravitational force. Now we know that work is calculated by force delta x cos of theta. And our force here is the weight force. Now, you can represent that with a W as well, but don't confuse the two W's. This is your work done, and this is the weight. Or if you just want to leave it as Fg, you can do that as well, so that it's clearer. Now, we know that the weight is mass times gravitational acceleration, delta x cos of theta. Now we know the mass of the block is 6 kilograms. We know the value for our gravitational constant. Delta x, we know that it moves a distance of 1.6 meters. So if we are substituting now, we've got mass is 6, gravity is 9.8, delta x is 1.6, cos of theta. Now what is our theta? If we look at the 6 kilogram, our weight force is acting downward, or the gravitational force is acting downward, and the block is moving 1.6 downward. So if and delta x are in the same direction. So we know that when our force and our distance are in the same direction, there is no difference in the angle between them, or there's no angle between them. So our theta here is simply 0 degrees. And we get there 94.08 joules. Now, looking at the last part of this question, the coefficient of kinetic friction between the 4 kilogram block and the horizontal surface is 0.4. Ignore the effects of air resistance. And 5.4, we want to use energy principles to calculate the speed of the 6 kilogram block when it falls through 1.6 meters while still attached to the 4 kilogram block. So what we have now is that this 6 kilogram block is now pulling downward for that 1.6 meters. So remember, this is a pulley two-body system. So the 6 kilogram is pulling downward, which means the 4 kilogram is going to move expectedly to the right. And we've got the coefficient of friction between the 4 kilogram and the table. So 5.4, we are using energy principles. Now we know that the work energy theorem states that your net work is equal to the change in kinetic energy. Now, there are many ways that we can use this energy equation or the work energy theorem to calculate what we need to calculate about this block system. If we look at the 6 kilogram block, we've seen that we've got gravity acting on that and the tension in the rope. So those were the two forces that we identified to be acting on the 6 kilogram block. So if we look at the net work done on that block or by that block, it will be the work done by the weight and the work done by the tension in the string. So we will have here the work done by gravity plus the work done by the tension. And that is equal to the change in kinetic energy will be your final kinetic energy minus the initial kinetic energy. So we would have half mvf squared minus a half mvi squared. We know that work done is the force times the distance delta x cos of theta. So the force involved with the work done due to gravity would be our weight force. Again, don't confuse this W for weight with this W for work. Now, we know that weight is equal to mass times gravity. So we can use that as the force involved in the work done due to gravity. So we have mg delta x cos of theta plus, now the work done due to tension would be the force, which is the tension, times delta x cos of theta, and that is equal to half mvf squared minus half mvi squared. And we know that vi is our initial velocity and The question states that initially the blocks are held at rest. So our initial velocity is going to be 0. So substituting our values in here, mass, we are looking at the 6 kilogram block. So that's going to be 6. Gravity is 9.8. Delta x, now we know that the block has moved down 1.6 meters. So here we have our distance delta x of 1.6 meters. So that's going to be 1.6 cos of, now what would our theta be? So the delta x is going downward and our force of gravity is acting downward. So force and delta x are in the same direction. So we don't have an angle between them. So our theta would be 0. Every time we have our force and the delta x in the same direction, theta is 0. So cos 0 degrees plus, we've got tension, we don't know what the tension is yet. Delta x again is 1.6 cos, now what would that theta be? So delta x is still downward, but tension acts upward. So we've got force in the opposite direction to delta x. So we've got that angle there of 180 degrees. So cos 180 degrees. And that is equal to a half, mass again is 6, Vf squared minus a half 6. And we said initial velocity is 0. Now we are looking to find Vf, which is the speed at which the 6 kilogram block falls. And we also, if we look at this equation, don't have a value for the tension. As I mentioned, there are various ways in which to approach this question. I find the simplest way would be to follow through with each step. So, final answer we are looking for is the Vf for the 6 kilogram. So we need to find now the tension force in the string. Now the simplest way to do that, we've got here a two-body pulley problem. And we know how to calculate our tension and acceleration using simultaneous equations for these two-body systems. So let's look at it. For the 4 kilogram, we've got the tension in the string and we've got friction. For the 6 kilogram, we've got the weight and the tension. So we can set up our force equations and solve them simultaneously. Now, for the 4 kilogram, we've seen that we've got the tension and we've got friction. So I'm just going to use small f for friction. So that will be T minus F is equal to mass times acceleration, our force equation. Now we know that the friction force, so this will be T minus friction. Now we aren't given the friction force itself, we are given the coefficient of friction. And we know that friction force is coefficient of friction times normal force, which is equal to mass times acceleration. Now the normal force for the 4 kilogram block would be acting that way and you'd have gravity acting that way. Now because the 4 kilogram block is moving along the table, it's not moving up and down, means that the normal force and the gravitational force are equal. So normal force here is going to be equal to the weight. So that means we've got T minus mu K mg equals to ma. And if we substitute values in there, we are going to have T minus 0.4, which was given as the coefficient of kinetic friction. Mass is 4. We're looking at the 4 kilogram block now. Gravity is always 9.8 is equal to mass again is 4 times acceleration. So that gives us our equation 1. For the 6 kilogram block, we just have the weight and the tension. So it's going to be weight minus tension is equal to mass times acceleration. And we know that weight is mass times gravity minus tension is equal to mass times acceleration. So substituting in there, here our mass is 6, gravity 9.8 minus T is equal to 6 times acceleration. And that gives us equation 2. So rearranging these from equation 1, we get that T is equal to 4A plus 0.4 times 4 times 9.8. We can call that equation 3. We already know how to solve these two-body problems. And we can sub equation 3 into equation 2 to solve for one of the variables. So we would have 6 times 9.8 minus T. Now we have 4A minus 0.4 times 4 times 9.8. And that is equal to 6A. So from this equation, we can solve for A because now we've brought it down to just one variable, which is the acceleration. And we get a value of 4.312 meters per second squared, which we can then substitute into equation 1 or equation 3 if you prefer. So let's make it equation 3. And we would end up with the T is equal to 4 into 4.312 plus 0.4 times 4 times 9.8. And we get T to 32.928 newtons. So there we have calculated what the value of the tension force is. Going back to our work energy theorem, we can now substitute for tension. So we would have 6 times 9.8, 1.6 cos of 0 degrees plus 32.928 times 1.6 cos of 180 degrees is equal to half 6 VF squared. And from there we can calculate VF. Don't forget to square root your answer because it's VF squared. And we end up with 3.715 or 72 meters per second. And that is the velocity with which the 6 kilogram block falls that distance of 1.6 meters.